Hello, welcome to the presentation of ShrinCage, 4D printing accessories that self-adapt. My name is Yang Yue. I'm a current graduate student at Zhejiang University. The development of low-cost FDM 3D printing has made personal fabrication accessible. When an off-the-shelf product does not meet demands, many people redesign and remake things on their own. However, fabricating an adaptation for an existing object still requires certain skills. Measuring errors and the lack of print quality of low-cost 3D printers usually lead to size mismatch and extra iteration. To accommodate the uncertainty, a jointing mechanism will be required for secured connection, which adds further complexity to the modeling and assembly process. We address these problems by designing ShrinCage to produce shrinkable attachments to fit and fasten the existing objects. It leaves enough margin of manufacturing errors and simplifies 3D modeling and assembly. The shape memory properties that ShrinCage relies on can be found on common 3D printing materials, in this case PLA. In the process of 3D printing, the thermoplastic filament is first heated through the extruder at 200 degrees Celsius. It is stretched with nozzle movement and is adhered to the platform. Therefore, after 3D printing, it can be heated above 60 degrees Celsius to relax the stretched polymer chains and thus release the build-up stress to shrink along with the printing direction. The shrunk state will be maintained after cooling. Both the infill structure and the outer shell affect the overall shape retention after shrinking. Both the infill rate and the slicing layer height affect the shrinkage ratio. We recommend to use 2 pairs of settings to achieve shrinkage ratios of 25% for shrinkable parts and 5% for non-shrinkable parts. The design pipeline of ShrinCage is friendly to novice makers. First, roughly measure the existing object with a ruler. A 3D scanner is no longer required. Next, model the adapter. We developed a design tool in which users can input the rough size of the object, select an attachment template, set the non-shrinkable parts if needed, and as a result, they will have the model ready for printing. Then, use the common material and any common FDM 3D printer to print. Finally, assemble the print and heat up the object in 90 degrees Celsius of hot water or hot air. After cooling, the spoon can be used with new grasping gesture. Here we show a variety of adaptation examples of ShrinCage. ShrinCage can change the appearance of existing objects. After heating and shrinking around the heel, the butterfly wings are strongly fixed to the high heel. ShrinCage caters to the special needs of certain populations, such as the elderly, children, and patients with hand disabilities. We apply ShrinCage to both zippers and keys to test the improved gripping performance. For daily objects that are incomplete, broken, or having parts missing, we can repair them and reuse them with ShrinCage. For example, the broken curtain can be fixed by reconnecting the two ends together. We can transform waste into shapes with new functionality. A discarded glass cup can be recycled as a mushroom-shaped pen holder. There is no adhesive involved in the joining process of ShrinCage, so the parts can be easily detached through the process of heating afterwards. We can also enhance the 3D printed parts with rich material properties by embedding items such as magnet, rubber, and stone. We implanted stones at the bottom to stabilize the phone stand. In the user study, all participants successfully designed and fabricated adaptations by using our ShrinCage system. Please refer to our paper for more details. I'd like to thank my co-author and all the collaborators who contributed along the way. Thanks for listening, and I hope you will try out ShrinCage yourself.